Hey guys, Evan here, and today we will be starting part C of our homework for our first two parts. We first good. I have it up right here. Let me share my screen so you guys can see. Um, there you go. So the first part, remember, we derived a single tank cross-sectional area to get our Laplace transform for our to we're trying to find the height for our a series of three tanks. For drainage tanks, we were trying to find the height for the last tank in the series of drainage tanks in the Laplace domain using our transfer functions. For the first part and the second part, we compared our um, transfer functions equations to the what was it the state space matrices to see how they compare and which system was better if the matrices were closer to our transfer functions that we derived, which we found out they were not. So now today, part C, our goal is to one, for the first three tanks in the series, we're liquid level. The third tank in the controller by adjusting the inlet flow in the first tank using proportional controller, found by trial and error through numerical solutions of the differential equations, the maximum value of the controller gain which is KC, beyond which the system will become unstable. For simplicity, the transfer function measurement device is GM. So basically, we will be deriving the system or deriving the equation to find the height for tank three. Um, but now we're using three transfer functions. We're using our controller, so we're incorporating a controller. A proportional controller. We're still using our process, which is our transfer function as well, that we derived in the first part, and we're using a measurement system as well. Okay, so we'll have three controllers. Um, okay, and then we'll also be putting our derivations into Python to see how this looks as well. And then later on, we'll be deriving a amplitude ratio for and phase lag of an open loop transfer function. Okay. But yeah, let's kind of get started with this. And at the end, we'll basically be at the end of all this, we will be drawing out a bodega diagram on Python as well. So we'll be visualizing this on Python using bodega diagram and showing the controller, the shift, the amplitude versus frequency plot, and then that's basically it. Yeah. Okay. So uh I will start with the first part. So we'll be doing three transfer functions. And using the proportional controller. Okay. So if I get out of this shaper, okay. And you know the usual spiel with the flashbangs on Zoom. I don't know why people doing this. They've been doing this for the whole semester. But okay. So I drew this basically this a diagram of how this system will look. So we actually start here. This is GP. So GP is our process. And I'll put it here. So GP is all the transfer functions. So this is our process. We have GC, who's our controller, and then GM, which is our measurement device. Okay. So we will start with this. So this is our GP. This is one. I'll just do one, two, three, so you guys can see as well. It's kind of hard to see, I know. So, oh no, this is not two. Well, in our system, this would be three. Okay, that's not a number, but yeah, I'm just gonna let it say myself. Okay. So this is our process. So we start with our process because we already know understand the unknown. That's why I already put our two conditions. So we know for our process for our three series tank, we had a inlet flow that comes into our process. It goes through the whole system of the three drainage tanks, and then we come out with a height H3 in the Laplace domain. Okay, we're still in the Laplace domain with this whole function with this diagram. So this whole thing is in the Laplace domain. That's why you see a capital H. So if we start with the GP, our process, remember we have our flow go in, Q in, goes out, we find our entire tank three. Okay. Well, for actual system in the manufacturing plant, we want to control this. We need to first put what we found. So if you want to find this, put this into a controller. Our height of our tank three, what we measure goes into a measurement system. So they're right here. This is our GM. This is our measurement. This is our measurement device for our process. So let's say we had like a distillation column, okay, and we want to measure again like the height of our tank three is in three columns. Okay, we will have a process, and then at the end we will see a receiver that goes into a measurement device, which is our GM. Our GM, our measurement device, then goes to a calibrator, which then shoots out our error. And our error is based on, well, first, the system that's coming in is that, of course, we have a set of height for our tank three, kind of like what we did for our Python. We had a set of height that we wanted to use for our tank three. So we input a set point for our height for our tank, and that goes into the calibrator as well. So we have a set point for our height, and then we also have the measurement device times the height that actually is coming out, the actual height from the tank. So that shoots out our error. Okay. And then from the error, we goes into the controller, which then the controller gives us our flow in. Okay. Now, like I said well, first what's error? So error in this case, error is equal to the height of the set point that we set minus the actual height that comes out times the measurement device. Okay. So that's error in this case. Okay. So if you wanted to actually like derive the equation for our height three, we first have to understand that this system is actually a closed loop system. Okay. So all this right is its own loop. It's closed. Okay. This is a closed loop. So if we did an overall balance from this system, we know that we have one flow coming in and one flow coming out. Okay. So if we say let's find H3, right? We have our H3 is equal to, we have the set point. We have H3 as the set point. And we know that is times our transfer function. So all the transfer functions together. So the transfer function for the closed loop is the overall transfer function of the closed loop. It is equal to our times our, so the transfer function of the whole loop. So this whole entire closed loop system times the height that we have the set point for is equal to the height that we will get from to our third tank. Okay. So this is the overall balance for H3, and this actually is the final answer. But if we want to actually find what the GL is, or our closest one is, we can actually derive this as well. But yeah, that's basically the closed loop system. So remember we're in the Laplace domain. This overall system is in a closed loop. I'm pretty sure it said that in the problem statement as well, but this is a closed loop. And the three factors that really determine it is the height of the set point that we put in, and then what we determine for our three transfer functions, our controller, our process system, and then our measurement device. Okay. So let's actually try to figure out what GL is. Okay. So we can actually start from the top. If we use the variables that were given in the problem statement, so GC, our controller, we know is equal to KC. We know our process system from what we did in the video before, that we got that K over tau of S plus 1 to the cubed which we know K is also equal to 1 over V. And we have GM is equal to 1. So if we let's just start with how we start this. So let's just do a balance. Let's just do the overall balance and get this. So we start from our our process. You know that our H3 is equal to our fluid times the transfer function of our process. Okay, GP. Okay. We know that our QN is actually equal to our transfer function of the controller, the proportional controller, times our error. And we know from up here that our error is equal to the height set point minus this height times the measurement device. Okay. So we set this all together. We plug in all the values for each set. You'll get that our height of the tank 3 would be equal to the proportional controller times the process times the controller times, and then we have our height, our set point height, minus the height, our actual height, tank 3 times the measurement device. Okay. Next we want to basically isolate our H3 because that's our desired product here. So what we would do, so we do H3. We actually factor both of these in. Then we'll multiply both of those both sides, and then we'll add this side over because it has the actual height to incorporate. So this would be plus GP times GC times GM times H3 is equal to GP times GC times the set point. And then we just factor this to H3. You will get H3, and then the parentheses will be 1 plus GP times GC times GM. And then the left hand, and then this is 1, so that's going to be in the parentheses anymore. Then everything on the left hand side will come down here. Okay, so we divide this by the other side. We get at H3, our height of their tank is equal to GP times GC times the set. I'll put that right last. Then divided by 1 plus GP times GC times GM times the height of the set point. Okay. Which actually, oh my gosh, why is it so bright? Why is it so bright? So bad. Okay, I think because my back's turned. Okay, so we have, let me restate this again. So we have the height of thing 3 is equal to our proportional controller times our process times our controller divided by 1 plus our process times our controller times our measurement system. Okay. Times overall times the height of set point. So this overall, if you actually compare what we have up here to this, it's the exact same. Because this right here is actually just our transfer function of our closed loop. So this is actually the equation to figure out how we can determine the height of 3 and actually determine our GL, our GCL, okay, our closed loop of our transfer function. Okay. But yeah, That's basically it. There's also we can also deduce this as well even more by incorporating um the limit at if we do the time limit. So I'll actually just do that as well. So we want to just find the simplified to G the closed loop function. Okay, I'll do it over here. So we want to just find the transfer function of closed loop. So G plus CL. We know that this is equal. We know it's equal to GP times GC divided by 1 plus GP times GC times GM. Okay. Now we can actually incorporate these terms into this equation. Okay. So if we incorporate the KC, the K divided by tau plus 1 and then 1, you will get that GCL is equal to KC times K over the tau S plus 1 to the cubed divided by 1 plus KC times K tau S plus 1 cubed. Okay, and then the GM is just equal to 1. Okay. My gosh, why is it so bright? Hopefully you guys can still see. I don't know why it keeps, I've been having lighting issues. But yeah, this is what we'll get to, okay? And we can actually, so like I said, we incorporate the time interval. We try to do our time variant. So we know that what is it? Limit of time. Okay, so we do the limit. I got this from Jay's video because that was actually the way I process and how to figure this out. So if we do the limit, the time to infinity, we know that that's just equal to our y. We get this function that for finding our y, select the time, which we know for this case, this is equal to the height for our tank 3. It's equal. Let me make this a little bit bigger. You guys can see more. I know it's kind of hard to see. Limit t to infinity. Okay. So like I said, if we do the time to put in time variant, you're trying to find when our time is equal to 0 to start off the controller. Because if we start off any measure in any process, you would start one before we start adding in time. So we start with our when first time was equal to infinity. That'll give us our y to t, which is our function, which is just equal to, in this case, our height in 3. Now we went into the Laplace domain because remember we're dealing with the Laplace domain. So this is actually just equal to the limit of when s, because remember s is Laplace, the Laplace, when equal to infinity as well. And we can say this is just s. Okay. Which we also know is just equal to our s times y, which is our Laplace function, which this is our y is equal to the Laplace of the change in height respect to time, which we know is just equal to our big H. Okay, so that's all it's equal to. So this is basically just S is equal S and H. And we can actually incorporate this. Like I just mentioned, we can state this when our limit is equal to 0. So when our S is equal to 0, we can incorporate this as well. So if we use this GC, our closed loop transfer function, in this equation, we can actually multiply this by our limit. When S is at 0, we just have S. Okay. Oh my gosh, let me accept that. Okay. We can incorporate our limit of S when S is equal to 0 into this equation. Okay. During this, we also have to multiply this also both by 1 over S. I know it's kind of simple, but we're trying to basically factor out our S here in this case. And by doing this, we can actually get our S and our tau times S to 0. which we know tau zero is equal to zero. So our bottom here for our tau s plus one is equal to one. So for both the bottom and top is equal to one. And this makes you basically makes our closed loop controller equal out to Kc times K divided by 1 plus Kc times K, right? Which is actually the final form. Oh no, it's not the final form. Hold on, I missed it. I forgot to also incorporate the limit. Because remember that we cancel our limit, but the limit still says so. When I close loop, when we are at times equal to zero in our process, we get that our K of Kc divided by 1 plus K of Kc, which is now, this is the final form for our closed loop function, transfer function. Okay. So we can actually just replug this in back into here. And for this, and we'll actually have our closed loop function for our closed loop transfer function in this case. But oh my gosh, it's flashbang. Hold on. I'm sorry. I don't know why I keep doing this. It's gonna happen later too. So just a warning for the later video you see. I have to redo the Python part for this. But yeah, that's it. This right here is our equation. You know, this is our closed loop equation for finding height three. Also this as well, more detail. And then the detail for our closed loop function and transfer function when incorporating time will give us that. So yeah, we'll actually be using all these in our Python as well. This is why I also want to write out this as well. We don't really need this for this part, but this will help for the Python. So I know you can't see it right now because it's lighting, but you hopefully wrote that out. But yeah, now we'll put this in Python and simulate this on the plot. Okay. And then I'll see you guys when we write out the Python. Okay. Bye. Hey guys, I'm back with another video. Back with another part of the first for our first video. I'm back from the whiteboard session, which we talked about the series. So we talked about our three transfer functions, the uh our GP, which is our process transfer function, our GM, which is our process function, measurement function, and then our GC, which is our controller for the series. And basically this part here, but we basically derive the equation how we find our height three, our height three for a drainage tank series if we use a controller, a proportional controller. So now we are just now putting what we derived into Python, and we're trying to find the maximum value for the controller gain. So our KC beyond which the system becomes unstable. Okay, so we're just trying to find what's our limit for KC in this case. Okay, so let's get started. Okay, first I want to start with what we would be going up with. So um, you see this is blank, which is kind of a first for me. Usually have at least our initial stuff, but the good thing about what we are doing today um is that we can use what we did for our part B series for our Python part, which we calculated when we just did the single series on the single drainage tank. All we did was it was a series, but we did just a series and not actually putting everything together and put what we found on Python into this actually for this part. So let me put what we have. So collab, Batori, open notebook, and then this should be net disability analysis. That's what we're currently doing. The other day. I did do it the other day. It may be this one. Let's try it out. Is it this one? It is, bingo. Okay, let me actually just call this shoot. I don't know. This is or or but what we be taking here, so of course we get our GitHub website. We'll take this, copy and paste, shift enter. We'll also take our libraries and all that good stuff. We'll take that. We will take our initial conditions, though they're not the same. We can edit that out later. We can like arrange them and delete what we need to delete, but we can take that. We can take our right hand side function because we need the right hand side function. That's the exact same, but we will be altering based on our conditions and what we're needing for our prompt statement. Um, we can take this as well, but it would be definitely deduced. And actually put it up here. Um, okay. We don't need our A and B because we're not dealing with space state matrices. We don't need this as well, transfer function. We can take our solver, see what we need in the solver. I don't know why I did that. I know it's gonna not work. Anyways, and then we can take our fig, take our plot statement. Okay. All right. So let's get started. So, um. just like I said, we are upload. Yeah, we're basically putting this our closed loop system into Python. Okay, so um, we know we need our cross section area for our tank for this tank. So we're talking about the process now, which is fine. We can keep that. We do not actually need our AH no more. Um, but actually will need B. So remember, our B is equal to 1 over B for K. We'll be using B instead of our AH, and we'll see why that later. But we can just say this is 0.26, something like that. We don't need gravity in this case, because that's for our leading, and we don't need that for now. And we don't need this as well. Okay. Well, we do need Q in initial steady state, but we actually put a value for this. So we can just say, what do you want our value to be? We can do like 0.75. That works. Yeah, 0.75. And then for our initial height, at steady state would be something different as well, because what we'll be doing, we want to capture the heights for all of our three tanks. So what we would do NP full, and we'll do 3 to basically say this would be the heights for all three tanks. And then what will be inside, what will the tanks be calculated to? It will be, what is it? It'll be our Q in initial steady state divided by RB. And that's one is wrong. Oh, I spelled it wrong here. Okay. So this statement here basically helps us by using the Q initial at steady state and dividing it by B, we can actually find the heights for our tanks, and then our heights initially be all the same. So we can just use the 3 here and do the NP full. So we did NP full to basically say all of our tanks will be at this height using this equation. Okay. Then we also find our steady state as well. We can find our set point for tank thing. We can calculate this as well. So this was just equal to, I'm just gonna say that we have captured, and then this should be our, we're gonna just do our last point. This is gonna be our -1 to capture the last point in our series. I mean for this row. So hit enter. All right. Now we'll move on to this. So our right hand function. So right hand side function. Okay. So as you see now, since we have a lot of new different initial conditions, we need to change our function to respect that. First, it starts with our dependent variables. We would, instead of having a flow initial, we'd be trying to find our height. So we can put h3 set point as the function as a dependent variable here.
Um, we do not need this anymore. We still need to capture this, but now we actually need to introduce error as well. So error, as we know, we already calculated error. Error is just equal to our, and this is why we use our, we put this for our dependent variable. It's h3 set point. So our height, our thing 3 set point that we put for our set point, minus our h3. Okay. In this case, we know that GM from our problem statement is equal to 1. So we can, if we want to say GM to, because we can, actually, let me just do that to keep it correct. GM is equal to 1. Just to make sure, like, we follow what we wrote down. Um, Even though it's equal to 1, so it has actually no change. If you want to change it later, we can do that. So, this is our error. So now from this, we can now actually find our flow. So I'm gonna just get rid of this and we'll copy and paste it later for the rest of the three. But what we can do to find our flow in is that we can actually just do B times our height 1. Okay. So kind of like we did this to find our expression, we just did to find our initial heights, we did our flow in divided by B. If you want to find our flows leaving, we can just do our height times our B. And there you go. So this will actually be able to give us all of our give us the flow leaving from tank 1 and going to tank 2. So we can actually just copy and paste this. And then this would be for 2 and we're in tank 3. And now we have all the flows for our tanks. I know, so simple and easy, right? Um, and now we can move to the change of our heights over time. Okay. This will also be different. And as you see, our one issue that we have here is that we don't actually have a flow coming in, like we don't have a set flow going in. Which is a problem. We need to find that. So what we can do is that we can actually put in Qn1 in our function. So Qn1, and we can set this equal to our Qn initial at steady state because that is. So what we have initially have here for our Qn is what will be going into our tanks. That's not changing. We're not changing our flow in, but that will be the flow that will be going into our first tank. So we're going to set that as our Qn1. And now we have this process here, which is correct. And we can do is we can just do this for the rest of them. So what we would do is that we would do Qn1 1 2, which is fine for the change of height for the change. Oh my gosh, I can't talk. Change in tank 2, we would do um just get rid of this. We have Qn1 minus, I think actually no, we just do Qn of 1 2. And then minus Q of 2 3 to find the change in height. And then this is fine as it is. And that's actually all we have to do. So for change of height for our tanks 1, 2, and 3, all we have to do is just take what was going in, subtract what's going out. There's no extra flows in like we have for our part B. We just have what's going in minus what's going out. So we can take from what we initially pour in and then subtract it from what's going out tank 1. We can take what's coming in from tank 2, going into tank 2 from tank 1, and subtract from whatever leaving tank 2 is going to tank 3. And then from tank 3, whatever coming in from tank 3, which is from tank 2, and then minus whatever is in tank 3. Okay. And of course, it's all getting divided by the cross-sectional area of each tanks, which each tank is the same size. So let's be AC for all of it. Okay. And then of course, we are taking the change of the heights and we're returning it back for the function to capture the data. Okay. Next part, our res. So our solve IVP for the system, we still need to do a solve IVP. But in this case, we'll be using tend and just stating a time range. We can just do 100. Yeah, we usually do 100. And everything is really mostly the same. To be honest. The only things we need to change, of course, this bad boy right here. This now will be our heights. So we're not using flows, we're doing height. So it'll just be our H initial, a steady state. and we'll be pl adding one. I forgot to show it actually on here, on the sheet that we worked out. I think did I show it on the whiteboard? It was in my notes. Let me see. From this is the next part. We're on the next part. Um, but basically we know that because remember we found the limit here that one's equal to the limit of KC of K. And we can actually apply that as well to our error. So we know that our error is equal to the third tank set point minus our um minus our H3, I mean our height at 3, our actual height at 3. And we actually set that equal to 1. Um I think yeah, we set that equal to 1. I forgot the reason why. But yes, it actually turns out that it comes with the equal that H3, our set point for our tank 3 minus our actual height for our tank is equal to 1. Um so if we do that, we can actually just add 1 to the system, and that we can it'll help solve for our function. Um okay. I know that didn't make that much sense. But I'm actually explaining a little bit more in the next video. Because I know that wasn't the best explanation. But I'll make a note and explain why we did the +1. But yeah, everything else is pretty much the same. Um, yeah. The 10, we changed our time because now it's to 0 to 100 from our 10. Our initial height is still our initial, yeah. Then the method is still I do, and this output is true because it's a continuous function. Restrict the time, of course, but we shift enter too many values unexpected. Now, what's the problem? We don't have that anymore. I forgot to shift enter. Oh, I forgot to shift enter. I forgot to shift enter everything. Okay. Okay. Now we should be good. Perfect. So now we can actually graph this out. And oh, I forgot to put KC. What am I doing? Okay, well, I just remember that. We forgot to actually grab KC because we're trying to find KC. Um, okay. So now I know there's a problem wrong because I didn't capture KC in none of my. That's actually interesting. I totally forgot about KC, and we need KC for this. Let me check. I'll be right back. Because now I just realized I didn't incorporate KC into our function, which we need KC for. Oh, I know why. Because we need it's right here. So it's our error. So we do error times our KC. Yeah, that's why. Because right here, remember, we find our flow in to our system from error times our control, our proportional controller, which is our KC, which is then give us our flow in. Yes, that makes more sense. Yes. Okay. So now we should enter that. That makes sense. We can control with the flow going in respectfully. Okay. Now, all right, now we should be good. So now, and you also need a T-plot because we're doing a plot is based from time perspective to our solver. So we need a time plot. So T-plot is equal to lens space, NP lens space. And we're gonna just do 0. Oh, I messed up. 0, 100. Sorry, I don't know. Let's do 100 again. That's fine. Here's 100, Okay. We got make subplots. We can actually take one of these out. So I'll just pound it. Okay. And then this our X will now be time blocked. Our Y would now still be rest solved, but this would be to T plot. And we're still trying to grab our last tank, so it'll be for the third tank. Remember, we go from 0, 1, 2. So in Python, so the 2 would be our third tank in our series. And then the name we can just say we don't need a name. Oh, we can put the name. Solve. It's called solve IDP. It's actually what we did in class as well. So you solve IDP. Okay, so this should work. Shift enter. That is not correct at all. Okay, that is not correct at all. Hmm. Interesting. Okay. I know there's definitely something wrong. I'll be back. I think it has to do with mine. And then you're not really incorporating casing. But I'll be back. And we'll figure out the problem. Okay, so I spent some time figuring out what was the problem. Way longer than I thought it would be. I went down a little bit of rabbit hole, but there's a few things so we get to update to correct this. One first actually starting, what can we say? Starting from our definition. I mean our right hand side function. So what let me go back to here. So what we actually need to add as well. So this part is correct. We do need error times our controller to find our flow in. But we also actually need to add, I mean, so we need to multiple have this error times our controller added to our initial flow going in. So we need to also put in our initial flow. I said state also going in to the function, going to the process to find our flow, our first flow into tank one. Okay. So that's the first thing we need to change. Second thing, I'm not sure if this is highlighted red or not. Hopefully this was, so we get back on track. Um, but we actually also need to change this as well. This needs to be our our height of tank three set point, the initial height of tank three set point, and then we added plus one. So we're just adding plus one to our height of tank three set point. So we're basically saying, um, yeah, actually, that's basically it. We're just saying we're just adding we're adding plus one to the height of the tank three set point. Yeah, that's it for this. And then for our T plot, I put 100, which it needs to be 10. That's a small mistake, and then everything else should work. So we do this again. This should work. Should enter. Why is it not working? Why is it doing this? Last time I did this, it's because I had disconnect, and run all there's been a lot of that. Like I said, I went down a little bit of rabbit hole. And went from one small thing to 20 minutes of trying to figure out what was the actual route. So hopefully this works now. This should be 100% correct. If not, it has to probably do something with the game of my solver. Um, yeah, hopefully this works. So I don't know what's the problem here. So, um, this could go a little bit longer than I hope it was took. Oh, come on. There we go. There we go. Okay. And we're stuck again. Okay, so we have our 10 T plots. Rest all two. Now we're into set point. We got this now. Let me increase the variables. That also may be a difference as well. Maybe 1.75. Let's do 0.9. I think it's what we did in class. Um, Maybe this will work. Oh, also, I forgot. I need to increase. Yeah, I have to increase one of the data points. So 500. It still didn't work. Let's disconnect again. Try this again. That's something, yeah, because you see it gets to extreme numbers, which it doesn't make sense. Still having problems. I thought this would fix shit. It worked when I did it, and it really just worked when I did it outside the video. Because if we do, let's copy and paste this and see what we get. See, so we get an image just jumps instead of that being like a collection of numbers. So I don't know why it's doing that. We'll be back again. Hopefully this is the last time. And then we will hopefully get this figured out. Well, I forgot the issue. I forgot to get rid of the equal sign. Um, yeah, that was the reason why it was causing issues. Because it made it just like a tuple instead of it actually like doing the excellent people in space. So we get rid of that, and now we had to because we had to delete disconnect the runtime and then rerun this all. I remember that I did that the first time when I was away to and it worked, but then I forgot that I put an equal sign again. So yeah, but now it should work. It should work. It definitely should work. Um, hopefully, hopefully. I'm just trying to calculate the maximum minimum. Yeah, man. Yeah, man. Um, okay, so now we have it working. Okay, so as you see now, this is basically our controller. And you see it in our system. It's oscillating a lot, which we don't want anyone to have be basically coming out to steady state. So what we can do, we can change our controller. We can put it to one. So if we change it to one, you see now it starts to steady out, which is kind of what we want. And we can also let me get rid of this. We can also actually like calculate this as well to see to compare the theoretical to actual in this case. So theoretical meaning our KC and then our we can actually calculate the difference in heights between our first and last tank. So um can we all we do is 1 divided by B for K because we know that's what are equal to our K. And our KC that's equal to um that's equal, that's equal to K divided by, and we actually was using this actually. So we know K is actually equal to 1 plus KC times plus K times K. And these are actually just 1. Is it B? Let me see, let me think. I'm pretty sure. What is it? It's K. Be right back. Okay, I'm back. Okay, so like I said, find our case, our controller KC. All it is KC is equal to K divided by 1 plus KC times K. And we're kind of just using the limit that we found down here to solve for this. So we can display KC, which will give us this number right here, 0.79, which is our controller. Um, and for this case, our theoretical controller. And then it's not the same what we have up here, but it's our theoretical, like, of course, our theoretical controller. But then we can actually calculate also our actual difference in height. So what we can do is we'll just do, and we can actually just copy and paste literally this. So we can take the height of tank 3 uh at the last, I mean, the when you take the height of tank 3 minus right, I just as I saw 9 plots and 0. What the heck? Oh, I forgot to do there. Gotcha. Okay. So we can take basically the difference in this is the last, this is capturing the height of the tank 3 and then the height of tank 1. Okay. So we do this. I actually just put 2 actually because it's the exact same. We do this, shift enter. Oh, there we go. That makes more sense. Yeah, let me go back to that. But we get the actual controller very actual controller value. Which is actually pretty good. It's not controller, it's not the controller value, but it's the height, I would say. But yeah, from doing this, that's why you can see that over time the system steadies out. Like it steadies out compared to what we had earlier when we had our controller set to 2. It was oscillating a lot, and that means the process steadily the controller steadily have to adjust to the changes flow. But now you see that the controller steadies out over time, which is kind of what we want to see. So the closer these two numbers are on the graph, you can kind of tell that are how the systems are. We want to get these numbers as close as possible. So right now this is pretty good. We can try to go lower to see what it will look like. We can do like 0.8, see if they'll still be kind of steady. It actually kind of looks better. My numbers don't say that though, but it definitely steadies out way more. Um, let's try. We are looking for the maximum, not minimum. So let's try the maximum. So let's do 1.5. A lot of oscillations, and our numbers are kind of the same, but they are off. They are off. They're not the same. They're off. Let's try to do 1.3 or 2.5 right in the middle. It's still oscillating a little bit. It's kind of starting to steady out over time, but we still need a lot more time. Let's do 1.2. See what that does. 1.2, kind of like the same thing, 1.25. We can try 1.1. 1.1, yeah, you start seeing more of a steady out. So I would say like the maximum in this case for the conditions that we have, um, the controller needs to be around 1 to 1.1 to for the system. That kind of is kind of our maximum controller range in this case, kind of low. I know the lower we go as well though, like when we did the 0.9, it actually did steady out way more. Even though our controller numbers didn't say that, but the best we had was 1. Of course that makes the most sense. But yeah, I would say the maximum we can go for the condition we have here is about 1 to 1.1. It's a maximum. Then lower, of course, you get more control. But yeah. Um, that's our maximum controller for this case when GM's equal to 1. And that's it for this part. Next part, we would derive an expression for amplitude ratio and phase lag. Okay. So I'll see you guys in that video. Hey y'all, Evan here again. Today, we are back, finishing out part C, at least the third part of part C, and then we're going to code it. I mean, actually, we're only on the second part of part C. Oh yeah, we're only on the second part of part C. But everything should start moving quickly for 3 and 4. But this time today we will be deriving the expression for amplitude ratio and phase lag of an open loop transfer function. You remember we'll be dealing with a closed loop transfer function system. Like for one on a series in a closed loop transfer function. But now that we're being an open loop transfer function. Function in the response is the sign input. Um, show the detail-wise substitution of S equal to JW yields the long-term sinusoidal, hope I'm saying that right, response for the system and the sign input. Okay. So, let's basically get this started. I did want to explain, okay, for this, because basically what we're doing is that we'll have a transfer function, basically represent as GS. And GS will represent the three transfer functions we had for our series, which would be our GP, which is again our process transfer function, our GM is our measurement transfer function, and then our GC, which is our our proportional control transfer function. So all those three combined will be equal out to GC in our example. Okay. Now, GC for this example has a formula for this, basically a polynomial formula, which I'll explain a little bit later. I wanted to show you online, but I couldn't find nothing. I think I didn't look hard enough probably. But I'm gonna show you write everything out and then I'll explain it a little bit more. Yeah, let's kind of get started. I'm gonna stop sharing and then we can share on my iPad. This works. Let me see. Oh, I gotta hold on. I had to enable something. Um, all participants. There you go. I don't know why on Zoom, but it forces you to like not everybody can share screen. So I gotta do that real quick. Let's stop first. Okay, start first. Let me see. It should work now. Perfect. All right, so now let's go to the notebook. I know the first part we did on whiteboard, but I could not go to the library. Well, I tried to, but I left my charger, so my computer died before I could write this on the whiteboard, sadly. But the iPad will do for today. So like I was saying, we started with the GS transfer function. So G of S, and if we're trying to first we're trying to find an amplitude ratio. So this is for amplitude ratio. Okay, and you can see everything perfect. Okay, amplitude ratio. Um, I'm sorry, clicked the wrong thing. Okay, so like I said, we have a GS. Um, which is our transfer functions for all three transfer functions that we had in the series. And we multiply this by our amplitude, like I kind of said. So it'd be amplitude times W of S squared plus W squared. And this is part of the polynomial I was also talking about, the polynomial formula. So GS in this polynomial form is actually equal to A1 over S plus B1. So this polynomial form, it basically is A to the n divided by S plus Bn. And it keeps going on for a continuous amount of time, basically to infinity, until it reaches, so it keeps going, so it'll be A2 over S plus B2. And this keeps going for a very long time until we get to the final. So it's basically to infinity until we reach our last part, which we get CS plus D 2S squared plus W squared, which equal out both our denominators from the left and right hand side. So this is basically our formula for the GS. We just input amplitude into this. But this is our polynomial for where we would start off for finding our amplitude ratio. And we want to actually the our goal here is to compare is try to merge our transfer function formula with our Laplace domain. Because if you remember, we are doing all this example in the Laplace domain. So we need to actually make this formula into the Laplace domain. So we can kind of relate this. So if you remember, uh, the the prompt basically asks us, so in the Laplace domain, you want to input our sign and for this. So we'll have our amplitude sign. So input sign for our amplitude for theta plus W expected time. I forgot what the Greek letter is I call, so I'm just gonna keep saying W. I know it's wrong. It's okay. But yes. This is what remember we had to relate the Laplace domain with the auto transfer function. Um, so by doing this, this actually equals out to a bar. So we put a bar now for the Laplace domain of sine. Is it cos first? Maybe cos. I'm pretty sure it's sine. Mm, I'm pretty sure it's sine. Okay, sine of theta. Yes. No, this is wrong. I knew I was wrong. Yeah, it's cos first. Yeah, it's cos. Oh, that doesn't make sense. So it's co eight. It's a over 2 times cos of theta plus the amplitude of the sine, amplitude times s times, the sine of theta, all divided by r squared plus w squared. And this actually just equals out to, so I'm gonna put this over here, equal out to, we'll guess it, S CS plus D over S squared plus W squared. So as you see, we have matching results here. So we can actually relate both of these terms, but we want to first kind of simplify them to the basis that we can, the simplify as much as we can before we relate both our transfer function formula and our Laplace domain, okay, to find our amplitude ratio. Okay. Because one will give us our amplitude in the transfer function, and then one will give us our amplitude in the Laplace domain. So that's basically what we're trying to do. So we can just go back to our amplitude ratio, our transfer function. Okay. And what we will do here is that we'll multiply both sides by s squared plus w squared. Let me zoom in so I don't take up so much space. But basically what we're gonna do is that we'll just multiply the denominator, the s squared plus w squared, to the numerator. So that will leave us with um transfer functions times RA, and now the s squared plus w squared for the amplitude as it goes away. So now we just have w is equal to, now we'll have a sum for all the polynomials. And the I is equal to 1. For A of n, so kind of like I said, A of n, S plus B of n times S squared plus W squared. Remember, I multiply by the numerator for everything in the formula. And then plus, now this is BCS plus D. Okay. Now, next, like our prompt also wanted us to say that we want to make our S equal to JW. Okay. So now we'll plug in JW for S. So S is equal to JW. And for J here, J is actually an imaginary number. So J, remember imaginary numbers, is equal to uh, square root of -1. Okay, like our imaginary numbers, imaginary numbers. It goes I is equal to square root of -1. I squared is equal to -1. I cubed is equal to 1. And then I to the fourth Oh, I forgot it was I for the 4 4, it's not gonna lie. But dates back to this. Um, we want to substitute J and JW for all of our S's. So if we do that, um, we will substitute it for here, here, and here. Now for the spot we have here for with our polynomials, it's squared, it is squared. So like I just said, we will have a -1 in this case, but -1 times W. So we'll have a -1 W squared here. So -1, so negative W squared plus W squared is equal to 0. So this whole polynomial, this whole sum of polynomials here goes to 0. Okay. So then we're left with uh transfer functions, a J, a W, times our amplitude is equal to CS. Well, C, we'll put the J out here on the outside of the C. CW plus RD variable. Okay. And now we just want our transfer function on this by we want to isolate our transfer function. Okay. So we'll divide by AW, our amplitude, and this will give us, let me see if I can scoot over a little bit. I can, perfect. This will give us our transfer function is equal to J CA, because the W's cancel out here, plus D of AW. Okay. All right. So this is where we have for our G, oh, I'm sorry, G of W. Okay. Okay. So this is basically what we have here for our transfer function. Uh, and what we can do, we can also relate this back and put this into imaginary. What's happening? Okay, sorry. My, I want to make sure I was still recording. Looked like something was bugged. Okay. Well, like what I was saying, we can relate our transfer function back to S and basically put this into imaginary terms, real terms. And these will be very important later on when we compare our Laplace domain to our transfer function. And we want to find a way to basically relate these terms and put these into Laplace domain. So what we can do is go back and put and use our transfer function g of s. And we know this is equal to, if we go back to our first video for part C and relate our three series terms, we know we can say that our transfer function here is equal to, what is it, Kc times K is divided by our tau of S plus 1 cubed. Okay. And this is from our series that we have. So all the three transfer functions combined will give you this. Okay. Now we know this is actually equal to our imaginary term, I, what is it? I of is Ji for imaginary term. So imaginary term, I plus R, our real term. Okay. And if you actually compare both of these two, you can see that we actually have like terms. That our C of A is equal to our I, and our DAW is equal to our R. Okay. So these are actually the same here in this case. So our C of A is our imaginary variable here, and our R is our real variable in this case for our G of S in our system, which we will use this later when we compare our system. But this is very important, and this is the main factor how we can relate both of the terms to get our amplitude ratio. All right, so now after finding this is basically all we need for transfer function before we go to our final step. But we need to go back to our Laplace domain. So in our Laplace domain, remember we had that we had the same basically output. We had the same solution, CS plus D divided by CS squared plus W squared. But we had to find a way to simplify this as well. We need to simplify our C and our D terms to kind of match what we have for our transfer functions. Okay. So what we can do, we can I move up this? I was wondering, oh, I cannot. It's withdraw. Okay. So I want to move this down. Um, I think if I do this, it'll be fine. Okay. So what we do, we want, like I just said, we want to basically simplify our CS and D terms. And we know, if you could look up here, that our CS is compared to our sine function here because we both have we see a S here, and which means we can relate both of those. So CS is equal to the sine function, and our D is equal to our cos. Okay, so we can actually write that down. So let's move this down. So we know that this is Laplace now that our C of S is equal to our amplitude, this is A bar of S, times sine theta. Okay. The S's cancel out. We divide both the S's out. Then we get that C is equal to the amplitude of sine of theta. Okay. And now if we go to D, like I just said, D is equal to um the amplitude cos of theta. All right. So now we have basically all we need to figure out the amplitude ratio. Okay. We have our relatable variables. We have our transfer function simplified and related to our imaginary real numbers. We have our Laplace domain for the C, and we have a Laplace domain of C and D in the sine and cos input in the sine input factored out into the simplified form for C and D, which you can relate to back for our transfer function. So now we can kind of start plugging stuff in. Okay. So as you see here, um, we can, like I said here, we can plug these, use C of A and put them here. So it'll actually give us, if we use this again, if we go back to transfer function, we can get that G of S is equal to C of A. Well, basically, I mean, that's the C of A. But it's basically equal to C plus D of W. Okay. So we're gonna let that here. And if we use these terms that we found here for our Laplace domain, we can say that C plus D of W is equal to, and we can divide this by W and it'd be fine. Yeah, it's no big deal. Because we have to relate the terms for D, we have to divide by W as well for this, which is again, it's okay. This would though give us uh A of sine of theta plus A cos of theta. Okay, perfect. Now, for this, we will actually want to square this as well. So if we square these out, so we square both sides, everything's squared, we will get that C squared plus D squared is equal to A bar squared sine squared of theta plus A bar cos squared of theta. Okay. We can factor out the A, and that will give us C squared plus DW squared is equal to A bar sine, parentheses sine, square root of theta plus cos squared of theta, which we know that's A squared plus cos squared, I mean sine squared plus cos squared is equal to 1. So this is literally just equal to 1. So we're left with A. So now we know that C, which is just equal to A. So now we know that C squared plus DW squared is equal to A bar. And we can actually relate this back to our imaginary numbers. So if we want to set this for our imaginary numbers as well, we can say that C squared plus DW squared is equal to um was it an A? I think I'm missing something. Let me think. I'm looking at my screen because it has literally what I was displaying on the screen. I think it's supposed to be an A somewhere. There is, yes. So this is actually supposed to be A of I plus A of R. So when we factor these out, the A's get canceled out with the C and D. So this is why we get the C and DW. Okay, which makes a lot more sense. Okay. So by using this, now we can lay back this right here and plug it down here, and we get that A squared, no bar, because it's the regular amplitude, not in the Laplace domain, plus A squared R. Okay. And we can, since we know these are the exact same, we can relate both of these two together, and we'll get that A bar is equal to A squared plus I squared, mean times I squared, plus A squared of R. Factor out the A's and put the A to the bottom. We get that, oh, this bar squared. It is. I forgot the squared here. Just put it squared. We get that A bar squared, amplitude of the Laplace domain squared, times the divided by the amplitude squared, is equal to our imaginary number squared plus our real number squared. And what we want to do is that we don't want the squares for our amplitude ratio. So we just square root this in both sides. And this will give us that. Oh, perfect. Right at the end of the page. Perfect. This will give us for our amplitude ratio now. That our amplitude ratio of A bar divided by A is equal to the square root of our imaginary number squared plus our real number squared. And this is the formula for our amplitude ratio. Okay. So that is our amplitude ratio. This is it right here. The Laplace domain of amplitude divided by the amplitude of the transfer function formula, which is equal to our imaginary number, each square root of our imaginary number squared plus our real number squared. Okay. Now to our phase lag, which is much simpler, much simpler. So phase lag, it's actually kind of just a two-step process. So for a phase lag, all we will do, kind of like our amplitude function, our amplitude, we will just do our C divided by our dW, which we know if we go back to what our Laplace sine and cosine functions are for C and D. We know that is just sine, A bar sine, theta divided by A bar of cos theta. And if you remember from geometry, sine divided by cos is equal to tan. So the A's cancel out, and we get that tan theta is equal to this expression, which we also know, again, that we know C divided by dW. We know that C in our transfer function formula, C is equal to I. So we have I, and we know that R is equal to D divided by W. So we know that is actually just equal to R. So you have I divided by R. Okay. So this is the part right here that we are looking at right here. Okay. And if we want theta by itself, because that's where you basically calculate our phase lag by theta. We'll do theta, and we basically move tan to the opposite side, to the right hand side. So we just do the inverse of tan, so arctangent. So we do theta is equal to arctangent of I divided by R. All right. And this is your equation right here for phase lag. I told you it'd be much simpler. We already had all the data that we needed. So this is our amplitude ratio, and this is our phase lag ratio. Okay. And we will use this now to model our Bode diagram in Python, which we will do in the next video. Okay, so I will see you guys over in Python. Hey everybody, Evan here back with the third part of part C. You remember our last video, we derived our amplitude ratio and our phase lag derivation over on the iPad, and now we're over at Python, where we will be putting what we derived from the iPad and creating our Bode diagram, which will be look like this. Um, um, yeah, which will look like this. Yeah. Which is on the top is the amplitude ratio and the bottom is phase lag. And for this, once we create our Venn diagram, we have to explain why our crossover frequency for it is at 1. And then also show that what if we change the KC, how would that affect the shift for our amplitude versus frequency plot? Okay. So let's get started. I already have everything pulled up here. I think I accidentally showed you guys this on our last Python video. Actually, I do remember I showed you guys this in the last Python, so we're just using this page here. What you see, we have our amplitude here, our amplitude ratio, and then our phase lag. Okay, so let's get started. First we need to put our W. So W is equal to NP log space, and we're doing it from 2 to -2 to 2. And we do 1,000 points. Okay. Shift enter. Oh, I need to make sure all this is running. I forgot. Yeah, it's my first time starting it for the day. So this will be an error. Just gotta rerun everything. Okay, but after this, next we will start importing our I and R. So we do our RI. So we're just basically where's that on here? I'm gonna highlight it so you guys can see it. If I can find it. Here we go. We would just state this next, our IR equation. Okay. Just run this here. The next, our IR, we know is equal to oh, we also have to state tau. Forgot because we need tau for this instance. So we know tau is equal to our cross section area, our area of the cross sectional area of the tank. Oh my gosh. And cross sectional area of the tank. Um divided by B. So that is our tau. So now we can use tau in our equation. So we have all the other terms from the other previous. So K times KC divided by tau times W, which we just stated, uh times 1J. There's 1J, we can just state that. We don't have to define it because it's not in our other previous line of code. But excuse me. But it's already inputted in Python, so as an imaginary number. So we can just state that as already. So yeah. And then +1. And then this is to the third power. Right. And then next we have to define I and R. So I we know is imaginary. So we just do NP dot imaginary, and it's for IR. And then R, we just do NP dot real, and it's also for our IR. Okay. Shift enter. This works. Perfect. Okay. Next we have to what's the next thing we have to do? Yeah, now we just go to our amplitude ratio. Okay. So we for our amplitude ratio, what we have to do? We basically define this as AR now for our amplitude ratio. An amplitude ratio is equal to what is it? It's arctangent. No, that's tau. That's so it's what is it? MP dot well, we had to do MP dot unwrap for this. I know that. So MP dot unwrap, I have it up here. It wraps it by taking I can't talk. By taking it wraps by taking the complement of a large deltas as respect to the period. So we use this because we actually have to put our amplitudes in degrees. So in Python, our what is it called? Our no, that's for our arctangent. We don't need to unwrap the AR. That's what we had to use the later phase. But for our AR, I believe all we have to do, and we have to state this. Would it be MP dot? Hmm, I'm going on a link right now. Hmm. Hmm. Okay, let me do phase, and then maybe it popped in my head. So I know the phase, like I was saying earlier, because we had to always calculate the phase because we're doing a comparison from our empty ratio and phase. We know our phase is equal to NP dot unwrap. Actually, I'll just start NP dot tangent. I'll just go for inside and work out tangent, arctangent, and we'll do two for the two variables, and then that will be I and R. And then also we have to make it into degrees because right now it's in radians. So we do 180 divided by pi, so NP pi. And then this will be in the NP dot unwrap. Like I said, and like I said earlier, it's the help with large deltas with respect to the periods. Um, so NP dot unwrap. Okay. And then our AR, I want to say it's NP dot absolute of IR. That sounds right. I think that's right. We can check it. We can plot this out actually. That's all we need for the first part. Is that it's pretty simple code. So let me just take this. No need to keep time block. Let me call this fig two. Let me just delete this. Um, and then we need rows actually. Oh no. Okay. So we need rows. So equal to one. Actually, rows is equal to two. Columns equal to one. I know, different than usual. Different than usual. Um, and then for our first scatter plot, we will be using W, and then we'll be using our AR, so our empty ratio. We don't need a name. We do need rows. This is the first row, and then column, second row. I mean, first column. Yeah. And then we can copy and paste this. And then the next one would just be our phase. And this will be in row two. Then next we have to update our axes for these because these are in log scale. So log update uh x-axis, and then type would be equal to log for a row equal to one, columns equal to one. Now I can actually just copy and paste this, and I put for the y-axis as well. So for our empty ratio, our log, this log scale for our x and y. And then for the uh phase lag plot, it's actually just our x. So we just have to put two here. And then lastly, just for our layout, fig dot update layout. Since we're doing two plots, our height equal to 600, width equal to 800. Actually, I do 600 too. I do 700. Right in the middle. Sweet spot. Template. Holy dark. And then what is the last one? We have to use dictic. Um, I forgot where though. What's the arguments if we do? Hmm. Let me look this up real quick. Update fig dot update layout probably. I'm just trying to see how we started off, like the all the things we can put in it. No question mark. If I want, I have to pull it from the dictionary. That's why. Um, Let me check, and then I'll be back. So yeah. Let me just check real quick, and I'll be right back. And also check our AR too, because I want to make sure that's correct. But yeah, I'll check, and I'll be back. Okay, so I figured it out. Looked at the code, and all it is just y-axis 2 is equal to the dictionary. So, and then we get dick tick is equal to 60. Okay. And then we also, I can put show legend. There's no legend. Equal to false. Okay. Let me bump this down. Okay. And then actually I was right for the AR. So hey, pat on the back. Okay, so now this should work, hopefully. You know what? List and that's an outer range. Huh? I never had this error before. What's the problem? Rows and columns that outer range indicating that you're trying to add trace subplots that does not exist in your fig. What are you talking about? This is right though. Hmm? I actually don't know what the problem is. I think this is totally fine. I think yeah, it should be right. I'm gonna check again. Actually, I've never seen this problem before. The row pair set is out of range, but it's in between our bounds. Yeah, I know, I actually don't know what to do with this error. I'm gonna check what the problem is. I'll be back. Okay, so I looked it and it's because I forgot to update the figs. It should be fig 2. Um, I just noticed that. I was wondering why it was a problem. It should work now. Uh, okay, so now, I mean, at least it's okay. Where? For which one? Do you mean GEO? Is show legend not a thing? I'm gonna just, every time I try to do show legend, it just never works for me. So I'm gonna just let it rock. Oh, perfect. It worked. It worked. Okay. Okay. So, oh, it's actually a really nice graph. Okay. 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 So yes, as you see, we were able, where's my, there you go. We are able to, find out our Bode diagram right here. It actually matches pretty well. It's not as, straight, but like it's more curved, but it's still our Bode diagram. Okay. So next, what we want to do is explain why frequency, our crossover frequency is at 1. Okay. So all crossover frequency is that it's the point where our uh basically our I can't talk. I can't talk. Okay, basically where our phase goes past negative 180. And then once it goes past negative 180, we see that it starts to curve back down. And that's where you also, if you look on the empty ratio, where you will see the curve start to develop on the empty ratio. Um, so once we actually get past negative 180, we will actually start seeing the effect the empty ratio. So it should be around -1. But as you see here, it's not close to -1. I don't know why. Um, yeah, it's actually at point 0.5. But we go here, zero point 0.5. Yeah, yeah, it's around here. So yeah, I like what, zero point 0.5, literally exactly at zero point 0.5. You start seeing the phase change. Which if we go to zero point 0.5 here, where is it at? Actually, maybe up here. No, it's not up here. Zero point 0.5. Yeah, let's go easy in here. Yeah, 0.53. Yeah. Okay. So at the 0.53, we only get a empty ratio is only at 0.349. Um, Theoretically, it should be at 1. So if I think we go here, okay, it's not a good example at all. But yeah, our concentration should be at 1. It's just depending on where. It's really just it depends on. It's really just a state where the 180 changes. Where our phase lag goes past 180. I think if I change my KC, that would work. Which I think, let me go to like 2. Does that work? Does that help? It does not. Mm, okay. Yeah, I really don't know. I actually decreased it. No, it's the same. It's the same. Um, but yeah, it's really just the concentration is basically the limit to where we are switched from negative 180 over. So right now we're about 5 degrees over. Like, yeah, 180 is like 5 degrees. So like when it gets to 1, well, I want it's what? That's a lot of degrees over. It's about what, 40 degrees over the one over R1. So it's kind of a lot. Um, hmm, Interesting. But yeah, now I saw quantum frequency is, and then show how changing KC shifts the amplitude versus frequency plot. So all our KC, like I said, like this is all this is purposes for is basically determining how much we can change the controller before our it explodes. Because we're trying to make it to stability, and the more we increase it, the more likelihood it's getting closer to explode. So like right now I have it at 2, and our controller's exploded basically. So if we decrease it, let's say let's go to zero point 0.5. We have stability in our graph. Hmm, There's not a big change actually. Let me see. Let me see if I got 3. What's the big difference? Okay, so basically the biggest difference as that I saw is that it moves our y-axis. So it actually, as you saw, we went to point 0.5. We actually started above 1 and above 0, which is impossible. Yeah, it's kind of impossible. So and basically, by changing our KC, it changes the our y-axis where our plot really like start like for this for our log scale, it started above 1. And for our degrees, it started above 0. It would be negative, but it started on the negative axis, or actually positive axis. But it does just shift our y for it shifts the slope up or down basically. It doesn't really affect the phase lag or the frequency, the crossover frequency. It just changes our basically our degrees uh for um for the plot. Like as we go up, as we decrease our KC, our degrees will be will decrease. So actually, would it change? I guess it would change the frequency a little bit. Yeah, it should theoretically by a little bit, not by a lot. But the more you increase it by a large amount, it would change a lot. But yeah, that's basically it. Now we can go to 4. We can generate the plot of the open loop response in the system. Generate the open loop response of a system to a sinusoidal sinusoidal input and show that the amplitude ratio at long terms is identical to what is determined via by the diagram. So we can do that next. Okay, so for the open loop response, all we would do is that now we are, let me go back to my sheet. We are basically taking our GS, we're going back to GS. So remember we did our JW, for the Bode diagram. Uh, but now we're just we're going back to our trigger function. So we're going back to there's basically this, our GS with using the polynomial form. Um, and getting our seeing the Bode diagram also correlates with that. So let's start with this. So we just do GS. And this is equal to um and we know this is just we'll just recopy this down, but not inputting J or W. So do K times KC divided by tau. Let me put this tau times S now plus 1. Again, S is like J, sorry, in Python. Um the third power. Okay. And then next, what we will do is that we have to define our y and x's for here. So we'll do t and y are equal to sim of gs, our function, and then we'll also be adding a lambda. This should be respect to t, and we do np sim because remember we're doing this sim. So no, I can't say this word. Oh my gosh, sinusoidal. So it'll be sine np sine of 1 t in time. And then this, we would have an n for a number of times, number of points we want. So we do 1,000. Okay. And this should work. I think I need a comma. Yeah. Shift enter. Now you have our x and y's. I can just recopy this again. We don't need a t-plot, same as last time. This would be fig 3. You don't need rows or columns. Our x's will now, let's be 3. Our x would just be our t. Our y will be our y. No, we don't need a name. And then we can also just take this update. We don't need DTech. Okay, I'm gonna make it to what? 800. Okay, hit enter. Oh, I forgot to put the 3. Bam. Okay, so now this is our open loop. This is now a open loop response. So like I said, so for these, the first three responses, you kind of see they're sporadic. These are actually the polynomials. So this is our A1 S plus D1. So these are just the peaks of these. So you see we have we have four of them. So runs four times in polynomial form until we get to our steady state, our CS plus D, where it balances and stables out throughout the rest of the function. Actually, I think it does it a couple more times. This is kind of also not exactly. So I'll say about five times it runs in the polynomial form. So it goes through a summation of five before it stables out. Um, into the CS plus D of S squared plus W squared. But yeah. If we want to relate these two, we can actually if we want to, oh my gosh, let me just zoom back out, scale it back up. So if we go to the tip of this, we get around 0.02, which we relate this back to our amplitude ratio. Um, we go back to 0.02, 0.02, we can see that it's actually about where one is at, which is actually good for us. This is means yeah, it's actually exactly I want, which means it's a stable the system is stable. So it's actually perfect. That means our KC kind of works for this. Oh, our KC is kind of too big, but for this though, it's stabled out to one. I wonder if we change our KC, will that also change? Let's go back to one. Okay. Um so yeah, we actually get a different, what is it now? It's about 0.06, 0.065. So yeah, just around one again, still. Still being like so. This actually tells us where we will have stability in our process. Um, so if we compare our open loop system to our Debye diagram, we can kind of correlate where we will find stability and where it would be close to the one frequency. So yeah. Um, that's about it. That's all for part C. I know it was very long. But yeah, that's about it. And I will see you guys for the last part for part D, where we will show our transfer function, the complex poles. Okay. All right. Let's see you guys later.